Alright, so hello and welcome everyone to week 5 of interactive live sessions for the course on fundamentals of convective heat transfer. The course is being offered by NPTEL and instructed by Professor Amaresh Dalal of Department of Mechanical Engineering, IIT Guwahati. My name is Debjit. I am a TA for this course and we shall be solving problems together. So let us begin with question number 1 of today's session. Question number 1 says that in a circular tube, the nature of fully developed velocity profile for laminar flow is what?
Pa-
Is it option A linear, option B parabolic, option C flat, or option D exponential?
Parabolic, sir.
Parabolic, correct. So it's a simple problem. So let me draw the profile. So if I have a circular tube like this, this being the axis. So in the fully developed region, the velocity profile would be something like this. And expression wise, it's given like this, that u of r can be written as uh, r naught squared by 4 mu minus dou p dou x. It can be written as dp dx as well, since pressure is only a function of x, and this would be r squared by r naught squared. So this is actually an expression of a parabola. So the velocity profile is parabolic. Fine, simple. Moving on to question number 2. Question number 2 says if there are 3 statements given, you have to consider them and then select which ones are correct. So the first statement is core velocity increases in the axial. Okay, and these statements are related to the developing flow inside a circular tube. So you have to consider the developing flow region. Now, statement 1 says core velocity increases in the axial direction. Statement 2 says the boundary layer thickness is equal to the radius of the tube. Uh, Statement 3 says the radial velocity component is 0. Now, among these three, which ones are correct? So, there are some possible combinations given. Option A, only one is correct. Option B, only two is correct. Option C, both 1 and 2 are correct. And option D, all of them. That is 1, 2, and 3, all are correct.
Sir, core velocity means it's outside the boundary layer. Am I right?
Yeah, correct.
So it is constant.
The thing is, let's say if I draw a pipe once again. So, here is the developing region. So here is the developing region, and this particular
No,
region, this is called the core region.
it is increasing, sir. It is increasing. Yes, I am wrong.
Yeah, so the velocity here is increasing.
So first is correct.
The first one is correct. Let's
Second is
consider.
wrong. Second is wrong.
Second is wrong because this is true only in the developed region.
Develop, correct.
So this is wrong.
Radial.
Last one, radial velocity component is 0. What do you think?
This 1 and
Okay,
both
so
1 and
now
2. Sir, option is अभी only one is correct है तो वहाँ 3 option ही नहीं है.
correct. So if we look at the options, then we can infer from that only one is correct would be the correct solution. But yes, the radial velocity component is also not 0. Why so? Because if we consider
Actually it
continuity
is
here,
not 0. That's why actually 1 and 3 should be correct.
yeah, no, uh, not 1 and 3 should be correct. 3 is wrong. Why is it so? Because if we consider any location here, so let's say we'll consider 2 points. One before crossing the boundary layer and one after crossing the boundary layer. So the thing is, the velocity here and the velocity here, if we consider u1 and u2, this u2 is less than u1 because of the boundary layer growing there, and it is becoming lesser than the free stream velocity. So that's why if we take a control volume like this, so since this u is slowing down, that means uh, within this control volume, the mass influx is more than the mass outflux in the x directions. So let me do this more correctly. So here is one velocity and here is another velocity, u2 here and u1 here. We know that u2 is less than u1, and these are all incompressible flow. So
Debjit sir, sorry to disturb you.
yeah,
Actually, when we are talking about u, it is the velocity in axial direction.
correct. U is the axial component, and there has to be a v in the radial component. Why
So
this v
actually,
should not be zero? That's what I'm trying to argue now. Yes. What's your
uh,
question?
what I learned today only, I have seen the videos.
Hmm.
Sir has explained entrance region separately, that is developing flow
Hmm.
and fully developed flow. So in
Yeah.
that, what he has mentioned in his slides PPTs,
Hmm.
ki VR is not equal to zero for entrance region. Why? Because
What is not
streamline
zero?
VR velocity in radial direction
Velocity in radial direction is
is not equal to zero. That is, streamlines are not parallel.
correct. Yeah. That's
So
what I'm trying to say. That the
okay.
radial velocity component is zero.
That is
This
zero.
statement, this
Yes. I
statement
got
is
it.
wrong. Okay.
Means it is
This
present.
statement,
Yes, I got it, sir. That
yeah.
yes.
So my argument, what I was trying to say here is that in this small control volume, there is a U1 coming in and a U2 going out, and U1 is more than U2. Correct.
Hmm.
So for mass balance to take place, there must be some outflux in the net outflux in the y direction, so that ultimately dou u dou x plus dou v dou y, or in this case dou v dou r, becomes equal to 0. Since there is a dou u dou x present across this boundary layer, or even before it, within the core region, there has to be a dou v dou r. And dou v dou r itself existing means that v is not zero in all locations. There has to be some finite v in at least some location.
Yes. Yes.
Make sense?
Yes. Got
So the answer to this question would be only
one.
one is correct.
Yes.
Okay. Moving on. Moving on to question number 3. Which of the following is true for thermal entrance length LT and hydrodynamic entrance length L suffix H? Is it
Prandtl number.
option of
Prandtl
Prandtl?
number. C.
Okay, that's a very quick answer. So option C, LT by LH is proportional to Prandtl number is the correct one. So the derivation was shown in class. I hope you remember it and no
Yes. Yes.
clarification is required.
Yes.
Okay. So we'll quickly move on to question number 4 as well. So question number 4 says, in an internal flow for uniform wall heat flux condition, the mean temperature varies. How does it vary? Linearly with x, independent of x, exponentially with x, or none of the above. So what is
Mm,
uniform heat flux condition? So I'll draw this.
uniform heat flux condition. No? Okay.
So there is a constant, Q wall.
Mm-hmm.
And consider this within the developed region only, not the developing region, fully developed region.
It is linear, sir.
It is linear, correct.
Yes.
So that's the correct answer. If we write down the expression for mean temperature, it's
TMX
Tn
is
of x equal to T wall of x.
TMI
Yeah,
plus TMI. No,
this would be
TMI
T
plus
wall or TMI.
no TMI inlet temperature.
Inlet temperature.
Internal flow है ना sir?
Yeah, okay.
It's
So
internal
TMI.
temperature plus heat flux into perimeter into axial distance x upon m dot Cp.
Correct. Correct.
So it is a linear. No exponential comes in. I think it is a uniform wall temperature case.
Yeah. So we can, deduce it if we remember the temperature profile. So for uniform heat flux, there is this linearly varying Tm, and if we consider this is the developing zone and this is the fully developed zone, so there would be a gradual change over here within the developing zone, and again this becomes linear, and this distance remains constant between Tm and Tw, the wall temperature and the mean temperature or the bulk flow temperature. This is this is for Q equal to constant, the constant heat flux condition. And for the other case where the wall temperature is constant, sorry, this Tw equal to constant, there uh, Tm starts from Tmi, whatever is the initial temperature, and then it varies exponentially. So at x tends to infinity, will it become equal? So it's an exponential decay of this gap between wall temperature and bulk temperature. Okay.
Yes, yes.
So remembering these graphs can remind us whether it varies linearly, like in this case, or exponentially, like in this case. Okay.
Yes.
Moving on. Question number 5. This is again an easy one. Which of the following is a favorable pressure gradient for avoiding flow reversal? Is it option
For
A dpdx less
avoiding
than 0? Is it B dpdx greater than 0? C dpdx equal to 0? Or none of the above?
less than 0.
Dpdx less than 0 is the correct answer. Yeah. So if I have a flow in this direction, my intention would be to keep P1 greater than P2 so
Hmm.
that any fluid element always experiences a force in the direction of flow. Otherwise, if P2 is greater than P1 and a flow is in this direction, so and we have a flow element like this experiences a flow in the this experiences a force in the reverse direction. So there's always a chance that the particle will turn back while moving. So that causes flow reversal and eddies, and that's not desirable because it causes losses and all. In some cases they are desirable, but in most cases they are not. At least to minimize pumping power and all that, it's not desirable. Okay, so simple thing. Moving on, the fanning friction coefficient for Hagen-Poiseuille flow is given by option A, Cf equal to 16 by Reynolds number. Okay, and this Reynolds number is with respect to D, the diameter of the circular tube or pipe, whatever you call it. So so what's the factor? Is it 16, 32, or 64, or none of the above? This is for the
Six,
fanning friction coefficient, or also known as the skin friction coefficient.
16 by RAD.
16 by ID. Let's have a look. Yeah, correct. So this is the correct one. Is the derivation or further clarification required, or are you clear with everything?
No, I haven't seen actually last video. Only last video is remaining.
Okay, so
Actually, it is
let's
coming.
try
But
to see this one. So I think we previously wrote down the velocity profile for this, uh, for flow through for laminar flow through a circular tube, also known as Hagen-Poiseuille flow. So this is given by U equal to R naught squared by 4 mu into minus dou p dou x into 1 minus R squared by R naught squared. Correct.
Mhm.
So, and okay, we will do one simplification, one further simplification. So the U mean, if we calculate that, boils down to R naught squared by 8 mu into minus dou p dou x. I'll quickly check if I'm doing this correctly. Yeah. Okay. So up next, okay, what do we want? We want this CF. CF is nothing but tau omega by half rho u infinity square. So this is nothing but non-dimensionalized wall shear stress. So now we have to calculate tau w. Tau w is given by mu into dou u dou r in this case. So this would be okay. And if we plug this in over here, um, okay. So if we plug this value of mean velocity over here, so we can simply again write down this as uh, 2 um into 1 minus r square by r naught square. So using this, differentiating this with respect to r, this becomes 2 and inside it would be minus 2r by r naught squared. And we want this at r equal to r naught, that is at the wall.
Sir, I'm not getting this expression. You have written um, and again you have written u. So
Yeah, this is the expression of u which I'm trying to differentiate. So 2 is the
but so
initial coefficient.
initially you have written one more u, na? Starting में. U is
No,
equal to r for mu.
that is mu, the coefficient of viscosity.
No. U is equal to r0 square upon 4 mu.
Where which expression I'm not sure.
The first one before um.
This one are you talking about or this
No.
one?
First, this one.
This one. Yeah. So
So how this is
u.
different? These two are different. Last one and first one.
So I'll name these equations. This is equation number one.
Huh?
This is two, and this is three.
Huh.
You're asking the difference between one and three.
Because both are u, na? Mm-hmm.
Yeah, both are u. Only thing I'm doing is this this value of or the mean velocity. I know
Hmm.
that, and if I
Okay. I got it. You have put in terms of mean velocity.
correct.
Yes.
So that way u can be written as 2 into into
Mm-hmm.
1 minus r squared over r naught squared. Okay. Now I'm differentiating this with respect to r in order to get the wall shear stress. Okay, there will be a negative sign here. Is this step clear now over here?
Yes. We want skin friction means we want at wall.
Yeah. So this if we write down and here r would become equal to r naught. This we have to remember that r equal to r naught. So this becomes 4 mu uh, and r naught squared gets cancelled out. So it would be divided by r naught. Okay.
Mm. Yes.
Now now let's try to write this thing down. And this won't be u infinity. This would be only. So now CF, I'm writing it down as okay. I'm simply replacing tau W over here. So we know that to be 4 mu by R naught, and under over here we have half rho and squared. Okay,
1 get cancelled.
1 gets cancelled. This 2, if we put it up, it becomes 8.
8.
Correct.
Mm.
And okay, so down here we will keep rho, we will keep and we will divide it by mu. Mu was in the numerator, we are bringing it down in the denominator. And over here we have r naught only. Let's write it down as 2 r naught,
Diameter.
which would
Mm.
be the diameter. So since we are adding this 2 here, there will be another 2 that is getting multiplied. And
Mm.
this entire thing, this can be
Is
written as
a
the
Reynolds number. Mm.
Reynolds number with respect to diameter, since we are using this 2r naught. So CF becomes 16 by RET, which is the option 1, option A.
Yes.
Okay,
Yes.
so this is the derivation. Moving on to question number 7. Flow variables are independent of the angular variation in an axisymmetric flow. Is this statement true or is it false?
Axis symmetric flow. Flow variable
Axisymmetric flow. This is the key word in this question. So
angular independent. So flow variables means what exactly? Velocity?
Flow variables means u, v, w in the directions, x, theta, and x. Sorry, not theta.
So
X,
it's true.
r, and phi.
It's true.
Yeah, it's true, right? So if we look at this kind of cylindrical polar system where this is x, sorry, where this is x, this is r, and you know the angular component we can call it as phi. So in axisymmetric flow, axisymmetric means that dou phi of anything. It could be any variable that is equal to zero. That's what this means. Symmetric about axis, axis symmetric. So all the flow variables, they are independent of the angular variation, this variation of phi in an axisymmetric flow. So that's why this would be true. So all flow variables, dou phi of anything. It could be u, it could be v, it could be w. All of them would be zero. Also pressure, if you consider it. Clear?
Yes.
So again, moving on. So question number 8 of today's session. In a fully developed temperature region, the fluid temperature varies radially and axially. Is it true or is it false? So yeah, again I have applied
Fully.
flow like this. There is some developing region initially, and then there is a developed region. Within this region, temperature, is it a function of both R and X? The fluid temperature, does it vary radially and axially?
Probably only radially.
So that means this is false because in question it said and no or is given. So even
Hmm.
if it's not a function of either of them, the statement becomes incorrect.
Just I will try to draw the boundary layer
Yeah,
because they have not mentioned constant wall and constant that, no? Mhm.
it could be anything. Take any example. Take constant temperature or constant flux, whatever you are more comfortable with.
Okay. True. It's true.
True, correct.
Hmm.
So, even in developed region, fluid temperature varies radially and actually it is the you know non-dimensionalized temperature, which becomes only a function of R and does not vary with X. So, for simplicity, let's look at the case with constant heat flux. Okay. So there also in that, forget about the developing zone. Even in the developed zone, the profile looks something like this, and even downstream, this sorry, what I'm even downstream the profile is similar, but uh, the temperature actually increases at all locations since there is a constant heat flux and more heat is being added. Is it clear?
Hmm. Sir, but what is the meaning of suppose we are taking a constant wall temperature condition, correct?
I have a small thing to attend to. Can I be back in a few minutes?
Yes, yes, please.
I'm sorry, yeah, just a few minutes. Yeah, hello. I'm so sorry for it. It a small
Mm.
matter to look into. Yes, you're asking a question.
In case of fully developed flow,
Hmm.
just 1 minute, sir. I am getting to your screen. In case of a fully developed flow for constant heat flux condition.
Hmm.
No.
Yeah.
For uniform wall temperature condition, not constant heat flux. Uniform wall temperature the profile of the velocity, just like velocity, temperature profile is also getting
Hmm.
same in fully developed.
Similar but not same. Since there is more heat being added to it, the temperature is increasing. If we go back and have a look at this one, wait, where we drew the temperature profiles. So any of this, which one would you like to consider? The constant temperature one?
I am
Constant
confusing with
temperature.
constant temperature condition where velocity profile and temperature profiles are parabolic in nature.
Uh, Forget about velocity. Let's look at temperature only here. Okay.
Yes.
So here, if we look at the bulk mean temperature, see this is increasing with x.
Hmm.
So
Okay.
in this case also, where we had a constant heat flux, there also this mean temperature. This is increasing with x, but the profile does not change after developing. So now, if I go back to you know my thing over here. So this temperatures, all these temperatures, these are getting increased. So let's say if at any particular uh, location, we will call this location, x comma x1 comma r, x1 comma r1. So t at x1 comma r1, let's say we know this, and it has traveled a bit downstream, this being the x direction, and we consider this location, which is t at x2 but r1 only,
Yes.
same radial coordinate, but
Hmm.
uh, an
So,
increased axial coordinate where this you know, x2 is greater than x1. Here this temperature would be greater than this
okay.
because more and more heat is being added.
So same is the case for this constant wall temperature condition also.
Similar thing there also happens. There is constant heat
Heat
being
addition.
added to the
Hmm.
fluid,
Yes.
so that's why it's increasing this whole profile. So if I draw this profile, this second one, let's say at section 2 and I have at section 1, I will draw this in a better way. So if I draw the profile of section 1 over here, so I have something like this. So I have something like this, correct?
Hmm.
And at section 2, I have a similar profile. This
Yes.
curvature and everything is same, but it's shifted towards the right.
Means
So the
only the thing
temperature
is
has increased.
it is parabolic. The
Yeah,
thickness of the boundary layer is
same.
radius full.
Yeah. Hmm.
Means thickness remains same. Only the thing is temperature go on adding, increasing.
Yeah.
Hmm.
Heat is getting added, temperature is increasing.
Yes.
Okay. And this increase is linear for constant heat flux and exponential for constant wall temperature
Hmm.
with respect to x. Okay, is this thing clear?
Yes.
But if I non-dimensionalize this, if I say that I'll take this t wall of x minus t of both x and r, and t wall of x minus tm, which is again a function of x. This function phi, the non-dimensional temperature, this is a function of radius only. So this, if I take a derivative with respect to x, this is not a function of x. This becomes 0.
Hmm.
So, so what does this mean? This means that these this temperature profiles, they are similar. So if I have some way to you know non-dimensionalize them, make those uh, similar things, make them same, so then that would not change.
Hmm.
Okay.
Okay. Okay.
Okay. Moving on, we move on to question number 9 of today's session. So, question number 9 says that water flows through a circular tube with a mean velocity of 0.2 meter per second. The velocity is given. The mean inlet temperature. Uh, okay, I have some typo here. The mean inlet temperature, mean inlet and out. Okay, I'll fix this. The mean inlet and outlet temperatures. Okay. So, are the slides visible? Yeah.
Hmm.
So, water flows through a circular tube with a mean velocity of 0.2 meter per second. The mean inlet and outlet temperatures are 20 degrees Celsius, sorry, and 80 degrees Celsius. The inside diameter of the pipe is given, the length is given, the wall is heated with a maximum heat flux of this much. Consider the flow to be laminar and fully developed. The maximum wall temperature is what? And other property data is also given: density of water, heat transfer coefficient, specific heat capacity.
Sir, hello.
Yeah.
Actually, in one assignment, the data is given for liquid water.
Hmm.
I'm not going to discuss the answer, but only the thing is, means I'm not asking the answer to you, but only the thing is their properties are not given in the problem.
So then you can assume it is it a numerical type question where not
No,
option but you have to put in
no,
some value.
no, there are no options. I want to put the values, but the problem is there, convective heat transfer coefficient is not there. So that I can't take, na.
No, that you can't assume.
Mm,
Uh,
let's see if there is any alternative method available or not.
yeah, let's try to do this. Then we can
Oh,
discuss the question if we have time.
oh,
I won't explicitly tell you the answer, but we can discuss the approach. I guess
oh,
that's legal.
yes, yes, yes. Water flows through a circular with a minimum of point of view. Okay.
Okay, I'll drop a few hints. So first of all, uh, so first
I'm
of all,
having
yeah.
expression of TWX I am having, but maximum temperature I'm not getting.
Okay. So
TWX in terms of TMI, that expression is there with me, but
can you try to draw the temperature profiles with respect to X?
for constant heat flux condition.
Yeah. Okay. Let's take constant heat flux condition. Let's forget about this thing. Take
Mhm.
constant heat flux condition. Can you draw the profile for it? For T mean TM and TW as well.
T T min is going to increase as you just told because heat is added.
Linearly, correct?
Linearly.
And what about T wall?
T wall is also it is a constant heat flux, na? So T
Yeah.
wall is getting increased.
So how is it getting increased? Linearly.
Yes, linearly.
So this would be T wall.
Hmm.
So we can consider x equal to 0 to say some x equal to L. Sorry, some x equal to L where this pipe is ending. Okay.
Hmm.
So where do you think what is the question? The maximum wall temperature. Where do you think the maximum wall temperature would be found?
It is at the end wall,
It is
end of.
at the end where x equal
Yes.
to L.
Hmm.
Correct. So here let's have a look. So we know the Q, we know the Q,
Yes, we know Q, we know H.
we know H as well. Uh, we know the T min out as well. I will call
So we have to
same
assume
as
H.
we have to assume.
H for fully developed flow is going to remain constant. Yes,
Yeah,
no?
that
Uh,
remains constant.
yes. So okay. So to TW at L minus at TM at L is equal to Q by H of L.
Correct. So if I write down this Q equal to H into this temperature difference T wall at x equal to L minus this
TM
Tm
at.
at outlet. We will call this one L as well. So
Mm,
we know this, and this. We can easily figure out this one. So
mm,
and this one would be that maximum temperature. So T wall. Now I will write the same thing as T wall max. We can write this as TML into would area
plus
can you roll over here? No, we
TML
are
plus.
yeah. This is this thing only. So ml plus q by h,
Yes.
right? So we know all these values. What is TML? This is 80 degrees Celsius plus q is zero point
Point 0.6
0.6,
into 10 raised to minus 4.
zero point 0.6 into 10 raised to minus 4, and h is given as 560. Can you do this calculation for me?
Just 184. It is 80 around, only 80.
Uh, Okay,
Because
no, here, no, one thing. Here, it's not zero point 0.6 into 10 raised to minus 4, it's 10 raised to
it's
plus
4,
4.
4, 4, 4. Yes, yes. It is going on.
Watt by centimeter square.
Yes, it's just one
So this would be 6,000
6.7.
by 560. It would be roughly around 10.
90.71.
Yeah, roughly
90.71.
around 10. So 90.71. Or you can write this as 91 degrees Celsius. This is the correct answer. Okay.
Yes, yes.
Okay, moving on to the last question of today's session, question 10. So this is also a numerical type question where it says that a system for heating water from an inlet temperature of this much, 20 degrees Celsius, to an outlet temperature of 60 degrees Celsius involves passing the water through a thick walled tube having inner and outer diameters so and so. The outer surface of the tube is well insulated. What does this mean? Any heat that is created, it moves to the fluid only. Now, the electrical heating within the wall provides for uniform heat generation of Q dot equal to 106 watt per meter cube. Mind these units, watt per meter cube. So there is a heat generation within the block, within the pipe itself. It's a thick walled tube, and within that there is a volumetric heat generation. Now, for a water flow rate of m dot equal to zero point 0.1 kg per second, the length of the tube to achieve the desired outlet temperature, which is given as 60 degrees Celsius, what must be the length of the pipe? So I'll draw a quick figure of this. So I have a thick pipe. There is a finite thickness like this. Okay, and within this pipe there is a heat generation. So that heat generation Q dot, triple prime volumetric heat generation, that's given 106 by watt per meter cube.
So it is not,
And
sir,
it's,
sir, most
yeah.
of the time what happens, it is, I think it is 10 raised to 6. It's a type of mistake.
Oh, this 106 you mean?
Hmm. Because I have seen so many problems of heat generation. Most of the time it is, if we are calculating per unit volume, na, the
Hmm.
values are not like this. Yeah, if you open any
Okay.
heat transfer book, you will
Okay.
generally find it is raised to power something,
Okay.
10 raised to
Okay.
power.
Then let's take that. We will go with it. 10 to the power 6 watt per meter cube. Okay.
Hmm.
The value doesn't matter, the.
Ha, ha, ha.
Okay. So let's take 10 to the power 6. Now, uh,
Because such
as
kind
a
of problem is asked in assignment also, but it is 10 raised to, means such kind power value is there.
power value. Okay, we'll take power value. Maybe there is some typo here. Anyway.
Hmm.
And okay,
Okay.
what else is said? That the outer surface of the tube that is well insulated. So
Yes.
there is no heat flowing this way since it's insulated. So whatever heat is getting generated here, it's flowing inwards within the flowing fluid. So now, and this fluid, so if this is the direction x, so I am saying that the temperature of the fluid here at the inlet is 20 degrees Celsius, and I don't care whatever the profile is inside. At the outlet it's 60 degrees Celsius.
Okay.
So there has been a heat generation, there has been a heat addition to the fluid, and as a result of that the temperature increases. So it's a simple matter of heat balance. So by doing that we have to figure out what should be the length of the pipe.
So heat added is equal to increase in internal energy MCP delta T.
mgp delta t.
And
And
heat
heat
added,
added,
it
that depends
is, you
on
can write
H.
H.
No, no. Forget about H because whatever heat is generated, that is added. We don't care about the rate of convection from
So
the.
we'll do like this, multiply by volume, you will get watt.
Correct. So this Q dot triple prime into volume of the pipe.
Hmm.
This is the total heat generated, and that is added to the fluid, and that becomes equal to m dot Cp delta T. Correct.
Yes.
So this one we know. This V we can write as the okay, the area into the length, and the area we can write as pi into, is it given in diameter?
I
Sorry,
think it is pi by 4 do square minus
minus
di square
di square,
into
correct,
length.
into length, and this should be equal to this into the delta t we know mo minus mi, correct. Okay, so
Hmm.
I'll move to the next page. I'll write the same thing down again. So I have pi by 4 t square minus di square into L equal to m dot into Cp into Pm out minus Pmi. We simply have to find out L. So let's put everything over there. So m dot Cp, this Mo minus Mi. Here pi by 4 d naught squared minus di squared. Putting all the values. So m dot is zero point
Point
0.1,
1.
Cp is 4179. Zero point 0.1 into 4179. This was 60 and 20. 60 and 20. Q dot we took as 10 to the power 6. This is pi by 4. This d naught squared minus di squared. These are 40 and 20 millimeters. So zero point 0.04 squared minus zero point 0.02 squared. Okay.
Hmm.
So this we can write as 4179. Okay, I'm simply writing it as 480. Simple approximation into 40. divided by, we have 10 raised to the power 6 into pi by 4 into this thing. So 0.04 square, that is 16 and 4 decimal places. So 0.0016 minus 0.0004. So this becomes 0.0012, or you can write as 1.2 into 10 to the power minus 3. So cancelling them, this becomes 10 raised to the power plus 3. And we can solve this point 3.
So do this super.
Taking another one, this becomes 3.
So
Is this divisible by 3? Let's try once. This would be 13, 28, 9 point something.
answer is something 17.73 meter, like that.
Let me check it out. Okay, then we have 100 here and pi here. Yeah, how much are you getting?
17.73.
17.73.
Okay, I will check with you. 139 into 40 divided by 100 divided by 3.142. 17.69 by yours.
Yeah, something
And
like
it
that.
is 17.73 meter.
In meters. Good. So we have reached to the end of the session today. Do you have any
Yes.
questions?
Yes, sir. I'm
Yeah,
having one
about that
question.
assignment question. Let's discuss that.
No, before that, one another question is there, sir.
Okay,
If
very
the
good.
velocity profile and temperature profile both are given, and I want to calculate bulk mean temperature.
Yeah.
So actually, I have seen one formula, but I am not clicking because here, so whatever sir has explained that derivation, in that derivation there is uh, uh, one formula, that is increase in internal energy. CPT is coming T, and
Okay.
integration in sign is there from. Actually, this is the condition of parallel plate channel flow. So integration is coming from minus h to plus h, means from lower boundary to upper boundary. That
Okay.
is,
Let's take a general case. We know the profiles. We know these are, u is some function of r and t is some function of r and x. We know that. Okay.
yeah. U
So
is a
what?
function of y and r. You can take r or
Okay.
y.
R or y, anyone. So
Uh,
let's take y
Here
for.
y only, because parallel plate channels are there.
Okay. So it's a co-ed flow, right?
Hmm.
So if it's a co-ed flow, give me a second. Okay. So it's a co-ed flow with a velocity profile like this. It could be parabolic, it could be something else as well. We don't care. So u is a function of y only, and t is a function of both x and y.
Hmm.
Whatever functions is there, those are known functions. We know them. Now, while calculating bulk mean temperature, what is the philosophy behind it? Philosophy behind it is that if I know the bulk mean temperature as well as the average U, I can multiply them and have a sense of what is the energy that is being transported, or the total heat flux through any section. So let's take this section for example. I have distributed U. There is a flow through it, and each particle has a certain temperature associated with it as well. So across this section, there is a flow of heat energy, correct?
Yes.
So this heat flux, this is something which I'm trying to estimate using bulk mean temperature as well as uh, the mean velocity. So what should be this? There should be rho Cp into, uh, sorry, I want to write this way. So there is a mass flux, and That mass is carrying some energy with it, so it should be m dot Cp into some Tm, some characteristic bulk mean temperature.
Yes.
Okay, and this m dot I can write that as rho into u bar into Cptm, where this u bar is again mean velocity. I'll write it as um, not u bar. This is mean velocity, and this is mean temperature or bulk mean temperature. Okay,
Hmm.
so as it comes to the derivation, so this q dot, this is how I'm trying to represent. And what is it actually? It's actually, it can be integrated as this way, so into some dA over A, and this thing, how can it be written? It's the heat energy transported within a small elemental volume, or across an elemental area. This can be written as rho Cp U into T dA, correct?
Hmm.
Now, this quantity and this quantity, they're equal. So I'll write this this quantity equal to this quantity. So rho Cp U dot M, no, not U dot, Um into Tm, that should be equal to integration over area rho Cp ut into dA. And how do we write we simply write as you know 1 by area into uda, correct?
Hmm. Hmm.
And this, if we assume constant properties all throughout, then this rho cp gets cancelled. So now we can simply write this as 1 by a uda into Tm equal to this integral utdA. This boils down to utdA divided by 1 by a uda. Now, in case of this, where y goes from 0 to h, and in this direction, the direction out of the paper, we take an unit over there. There, this thing can be written this way. Instead of integrating over a, we can integrate over y going from 0 to h. Sorry, this is dy, and under here, this is 1 by a 0 to h u dy. This is the formula for Tm.
This formula I have seen in derivation, but only
Instead of a, this would be h, or 2h for that matter. It would go from minus h to h. Sorry, these limits are wrong. Okay, where is the problem? Where are you experiencing problem?
mm, so it is minus h to h. So
Yeah,
upper limit and lower limit we have to put. But now u and t are given in terms of y. So
yeah,
we have to multiply both.
yeah. We have to multiply both. So uh, it would be better if we take an example. No, if we, let's say, this is not writing it as u of y. Let's say this is some sine of y, and this is some cos of y, not a function of x, just a function of y. Let's say,
Hmm.
for the sake of argument. So
Okay.
in that case, you would actually plug in those uh, functions over here. U would be replaced as sine of y, into t would be as cos of y dy, and then over here whatever area we have, and in place of u we would actually put the functional form of y.
Hmm. Hmm. Hmm.
This is a arbitrary example where I took
Yes, yes,
tangential
yes, yes,
functions
sure.
out of the blue, but it could be any function. It could be parabolic, linear, anything, polynomial, whatever.
Mm-hmm. So here we have to, in uppercase, we have to put the limit, upper limit as h and lower limit as minus h.
That depends on the geometry.
In
Depending on
the
the geometry.
parallel plate case,
In the
this
parallel
one.
plate, yeah. So we have two parallel plates. I'm taking, the coordinate system like this: x over here, y over here, and y goes from minus h to plus h. And in this case,
So for example, it is a 10 centimeter dia. Okay.
not a diameter, but
And
the
sorry,
distance between.
height.
Yeah,
So it
yeah.
is going from minus 5 to 5,
Minus
positive
5
5.
to 5. Correct.
And below 1 by twice h means it comes as 10 centimeter.
10 on
1 by 10. Okay.
correct. Similarly, if instead of taking the origin here, if I would have taken the origin here, then y would run from 0 to h then being the actual distance between them, or 10 centimeter, like the example that you cited.
So
In
at
that
the
case,
end, it is going
it depends
same.
on geometry and choice of your origin.
The same answer will come.
Same answer will come.
Yes. Okay. And
Why do we take this, origin in between? The reason is from 0 to h and 0 to minus h, these profiles are symmetric. So it
Mhm.
simplifies down our map.
Okay.
Correct. Okay. Anything else? Any other question?
Okay. Actually, that question where data is not given.
Okay. So tell me whatever is given to you. Okay.
Mass flow rate is there.
I'll try to do it
I will
here.
not tell you value, only
Okay. Anyway,
data.
mass flow rate is
Mass flow
given.
rate is given. Diameter is given. Tube diameter. Length is given.
Hmm.
Mm, Water entry temperature is given. Inlet.
Hmm.
And surface temperature. Constant wall temperature condition is there. Surface temperature is given.
This is also given.
And
Okay.
ask is outlet temperature.
So this is simple, right? Uh, okay.
The
So
constant wall.
everything is given.
It is uniform wall temperature case, na? Surface temperature is only single value is given.
Yeah. So this would
So,
be the thing, right? So this
so whatever.
temperature is given. This temperature is asked for.
So I am having a doubt because I am having one formula with me. TMX. Okay.
EMX.
TM at X means at outlet. That is
Got
L
it.
is equal to TW wall temperature I know plus now it is exponential variation na, because it is uniform wall temperature case.
So e
So
to the
T
power minus.
so TMI minus TW
Okay. Sorry, that thing was there. TMI minus
minus
TW
TW
divided
bracket
by.
close नहीं bracket close है
Okay.
no divided by bracket close e raised to minus P h bar x upon m dot cp
Upon m dot cp. So your thing is this h bar is not given. How will I find it
and
out?
specific heat is not there.
It's water told, right?
Okay, water is I think 4.187.
So you know the CP. You can guess the CP. H bar is not given.
And x is L that we can take.
Yeah, X is L. That's fine. Mm, mm, I'm not sure. I don't know how to help you on this one.
Just minute. Perimeter pi d into
It
x
has a
minus
constant
between
wall temperature, right?
q. Hmm. That's why actually it is means instead of constant wall, if it is heat flux, H parameter is not coming in the
It is
equation.
not coming
Hmm.
there. Here also there might be some step in between where you
Mm-hmm.
can calculate the h as a function of x and then take an average.
Probably I have missed that video. Probably H we have to calculate us initially, and then we have to
Yeah,
put in that
yeah. There
probably.
has to be an intermediate step where you are
Mm-hmm.
calculating h and then plugging that
Mm-hmm.
value.
Okay, okay. ठीक है sir. Okay,
Look into
that's
it. Okay. If you have any issues, we can discuss later. I'll also look into it. I don't have a ready-made answer for you right now.
no, not necessary. Okay, I will try it, but
Okay. All the best.
okay,
Bye and thanks. It has been a
thank you, sir.
great session.
Thank you, sir. Thank you, thank you.
Thanks a lot. Okay.